All right, so taking a look at example 2. It says that we have a man who's 6 feet tall and he's walking at a rate of 5 feet per second towards a light pole that's 16 feet tall. They're asking us for 2 pieces of information here. Part A wants to know at what rate is the tip of his shadow moving when he's 10 feet from the base of the light. And part B wants to know at what rate is the length of his shadow moving when he is 10 feet from the base of the height. So we're actually looking for 2 different pieces of information in this. So again, I'm going to start by drawing my picture. I have a man that's 6 feet tall, and he's walking towards a light pole that's 16 feet tall. So here's my light pole, 16 feet tall. And then I have a man who is 6 feet tall, and he is walking towards that light pole. And it says that he's walking towards that light pole at a rate of 5 feet per second. I'm wanting to know what is the rate at which the tip of his shadow is moving, and I'm wanting to know what is the rate at which the length of his shadow is changing. So as he's walking towards this light pole, the light is hitting him and it's casting a shadow here on the ground. So let's just kind of draw that shadow. So as he's walking, he's leaving a shadow on the ground. By the way, the man is 6 feet, so we'll go ahead and put that information in. So we need to kind of define some different values here. We know that we're looking for the rate at which the tip of his shadow is moving. We know that we're looking for the rate at which the length of his shadow is moving. And they have given us the rate at which he is walking towards the light pole. So I'm going to start with that piece of information. He is walking towards the light pole at a rate of 5 feet per second, which means that the distance between the man and the light pole is decreasing at a rate of 5 feet per second. So I'm going to need some kind of variable to represent that distance. I'm going to let x, call it x, represent the distance that the man is from the light pole at any time. And of course that value is changing as he's walking towards the light pole. That value is decreasing. So they've given us the rate of change of the distance that he is from the light pole. We called it x with respect to t. And they've told us that that rate, that distance, should be decreasing because he's walking towards the pole at a rate of 5 feet per second. So that's the rate of change that we're given. We want to know how fast is the tip of his shadow moving when he's 10 feet from the base of the light. So if we go back to our picture, here's the tip of his shadow. We want to know how fast that's moving. And to know how fast that's moving, we need something that's going to be stationary. So we can kind of measure relative to what. And in this problem, our stationary object is the pole. The man is moving. So we want to know, if we want to know how fast this is moving, we can measure it from the light pole because that part's not changing. So I'm going to call the distance from the tip of his shadow to the light pole A. So we want to find how fast this is changing because that'll tell us how fast the tip of his shadow is moving. We want to find dA dt. And specifically, we want to find that when he is 10 feet from the base of the light. So x is how far he is from the base of the light when x equals 10 feet. So what we need is some kind of relationship between x, how far he is from the light, and A, how far the tip of his shadow is from the light. And so if I just kind of redraw what's happening here, this is 16 feet, this is 6 feet. The distance from here to here is x. The distance from there to there is a. And so I know that a, the total distance, is going to equal the distance that he is from the pole plus the distance from here to here. And the distance from here to here is going to be the length of his shadow. So the length of his shadow is also going to be changing as he's walking towards the pole. So I can't really give it a number. Since it's changing, I need to come up with some variable that represents the length of his shadow. So I'm going to go with z. You can call it whatever you want. I'm going to go with z. So z represents the length of his shadow. X represents the distance that he is from the light pole. Both of those things are changing as he's moving towards the light pole. And A represents the total of those two, the total distance that the tip of his shadow is from his light pole. So if I wanted to come up with a relationship that relates A and X, the easiest relationship we have is that A equals X plus Z. And so that relates the two variables that we know about. We know about the rate of change of x. We want to know about the rate of change of z. But it also introduces the problem of this extra variable, z. We need something that relates just a and x. So if I go back to my problem and I look for ideas, I notice again that I have similar triangles. I have a big triangle whose base is A and whose height is 16. And then I have this embedded smaller similar triangle in it whose base is Z and whose height is 6. So I can set up proportions here. I know that the height and the base on this are going to be proportionate to the height and the base on this. So I said that 16 over A, the height of our big triangle over the base of our big triangle, is proportionate to 6 over Z, the height of our little triangle and the base of our little triangle. I'm wanting to eliminate the variable z in this problem. So if I were to cross multiply, I would have that 16 times z is equal to a, or 6 times a, 6 times a, so then z would be equal to 6 divided by 16 times a, or if we reduce that, we would have 3 over 8 times a. So now if I go back to my original equation, I'm going to write it up here so I have more room. A equals x plus z. Now I know that z is equal to 3/8 a. So I have a equals x plus 3/8 a. So I have 1a, or 8/8 a. If I subtract 3/8 a, then I have that 5/8 a is equal to x. So now I finally have an equation that relates the variable whose rate of change I know, x, and the variable whose rate of change I don't know, a. So now I'm ready to look at the relationship between those rates of change. I am ready to differentiate everything. Let's put this one. I am ready to differentiate everything with respect to t. So the derivative of 5/8 a with respect to t will be 5/8 times the derivative of a with respect to t. That's what I'm looking for. If I differentiate x with respect to t, I get dx dt, which is the rate that I know. So now I know that dx dt is -5, so I have 5/8 times dA dt equals dx dt, which is -5. So if I multiply both sides by 8/5, I get that dA dt is -8. And again, we're talking about length here, so that will be in feet per second. The reason that we get a negative here is because we're talking about A, the total distance between the tip of his shadow and the pole. So what we're saying is that as he is walking towards the pole at a rate of 5 feet per second, the tip of his shadow will be moving towards the pole at a rate of 8 feet per second. So I'm just going to write that out real quick. The tip of his shadow is moving toward the pole at a rate of 8 feet per second. Part B is also related to the same setup, but in this one, they want to know what's the rate at which the length of his shadow is moving when he's 10 feet from the base of the pole. So we are still given the same rate of change. We are given the rate at which he's walking towards the pole. So that's the rate of change of his distance from the pole, x with respect to t. That's still -5 feet per second. But this time, they want us to find the rate of change of the length of his shadow. And if we go back to our original setup, we called the length of his shadow z. So we're looking for the rate of change of the length of his shadow, z, with respect to time, t, when he's 10 feet from the base of the pole. So when x, the distance that he is from the pole, is 10 feet. So at the same instant as part A, but now we're looking for a different rate of change. So again, I'm going to start back with my original relationship that actually related all three variables. I know that A is equal to x plus z. This time, though, I'm wanting to know about dx dt and dz dt. So this time, I need to get rid of A. Well, we said before that z is equal to 3/8 times A. Well, if that's true, then A is equal to 8/3 times Z. So we can use that information now to remove A from our equation. So instead of A, I'm going to put 8/3 Z. So if I have 8/3 and I remove 1 Z, 3/3, 8/3 minus 3/3 is going to give me 5/3 Z is equal to x. Now I've got my equation down to the variable whose rate I know and the variable whose rate I want to know. So now I'm ready to differentiate. So now I'm going to differentiate everything with respect to t. So I have 5/3 times the derivative of z with respect to t, dz dt, equals the derivative of x with respect to t, dx dt. I know that dx dt is 5, so I can substitute that in. I have 5/3 dz dt equals dx dt, which is -5. So if I multiply that by 3/5 on both sides, I get that dz dt would be equal to -3 feet per second. So the length of a shadow is decreasing at a rate of 3 feet per second. Now, it's kind of a quick side note. Notice that both of these were at the same instant when x was equal to 10 feet. So if I went back to my original setup, a equals x plus z. If I would have taken the derivative with respect to t of everything and not eliminated the third variable, I would have had that dA dt is equal to dx dt plus dz dt. In the previous problem, we had already determined that dA dt was -8 feet per second when x was equal to 10. We know that dx dt is equal to -5 feet per second. And notice what would have happened. Because I knew dA dt at the exact instant that I was looking for dz dt, if I had added the 5 to both sides, that's a plus, not a t. If I had added the 5 to both sides, I would have gotten -3 is equal to dz dt. So even if I hadn't removed that third variable here, because I actually knew the rate of change of A with respect to t at this instant, I still would have gotten the exact same answer. The only thing that I would caution you on is if you make a mistake up here and you get the wrong rate of change for A, then that mistake would carry over to here and you wouldn't get the correct answer. You would still get full credit for following the process correctly, but your answer would be incorrect, which would be a problem if you were looking at like a multiple choice. So in a free response question, if your setup was right and you took the wrong answer and applied it correctly here, then you'd still get the full points. But be careful about that, especially on multiple choice, because again, an error in your previous step could have carried over. By eliminating the variable from the beginning, we didn't have to worry about using dA dt at all. But because we knew what dA dt was when x was 10, we could have followed along that same process as well to solve.